Hi everyone, so here we are again. So today we are going just to solve some, we're just going to continue solving separable method, okay? So here we have some exercise, okay? We are going to solve applying separable method, okay? Just to saying that you can solve first order and first degree ordinary differentiation equation applying, okay, applying any other method, okay. It doesn't mean that this exercise can only be solved by separable method. This can be solved by separable method, okay, and also can be solved by how can I say, the integration factor, okay, apply integration factor method and so on and on, okay. As long as this differentiation equation is how can I say, is satisfying any of many of those method to solve, you can solve this by any of this method, okay. But the most important thing is that you have to check the condition before start solving, okay. Yeah. Okay, now let us just keep on with this exercise. Suppose here we have this one, x y squared plus x dx and y x squared y dy. So separable method, it is nothing more than we are going to separate, okay, the function of x has to be with differentiation of x and the function of y must be with differentiation of y. Just like this, okay. In this way, what we are going to do, okay, let us just solve this one. For the first exercise here, suppose here we have this one. For the first exercise is, I have x, okay, x plus, okay, x plus, okay, it is x plus, then x y square dx plus y plus x square y dy equal to 0. This is the first equation, okay. Is that the first thing is that, okay, I have to transform this equation in a way, I have to reduce this equation in this way, okay, f of x and f of y, okay, just this one. So is that possible? Yes, let us see. So here we have common factor and common factor x, and here 1 plus y square, and here dx plus y, also 1 plus x square, and dy equal to 0. So just by seeing, I can see that this can be differentiable in this form. This can be just aggruppated in this form. It is possible to aggregate this function of y with this y and this function of x with this x. So what we have to do, yeah, it's up on you, okay, it's up on you. You can just come here, divide it all by this and this, yeah. But I will do this one. It will be x 1 plus y square dx equal to minus, okay, minus what? Minus y 1 plus x square dy. Is that okay? Nice. So what's the next step? Okay, this y is negative, okay, this is okay, this one can be negative from here, okay, this is up on you, it's up on you. So what I'm going to do, I will just take this negative to this x, okay, to the function of x and not the function of y. It's my choice, okay, it's up on you. It will not interfere in the exercise any longer. It will not change anything in the solution, in the final solution. So see, okay, I'm making this one minus x, okay, and here it's minus x, just multiply by minus 1, this will be y, okay, positive, and here 1 plus y square dy, and here it will be the same, okay, it will be minus x dx upon 1 plus x squared, okay, because I just put this 1 plus minus square, okay, this negative high, okay, minus negative here, negative come here, it's okay, like multiply by minus 1, it will be negative, it will be positive. Then this 1 plus x square is a function of x, go with differentiation of x, 1 plus y squared is a function of y. Go with differentiation of y, just like this. Then here, just apply integration both sides. Okay, integrate both sides. Here you have dx and dx here. 1 plus x squared equal to the same integration y dy, okay, upon 1 plus y squared. Now here what you have to do, this one just add 2 here, take 2. It's okay. So this one will be the same as minus 1 by 2 integration of differentiation of 1 plus x squared and 1 plus x squared equal to 1 by 2 differentiation of the 1 plus y squared and here 1 plus y squared. Okay, this is equal to minus 1 by 2 ln of 1 plus x squared plus c, and this will be equal to 1 by 2 ln of 1 plus y squared. Is that okay? Nice. This is the solution for this equation, the general solution for this equation. You can just play a little bit. If you just suppose you can just join this guy and this guy, okay? It is negative, go there positive, and then multiply this by 2, all by 2. Multiply all by 2, okay? What you're going to have. First, send this one in here. This will be 1 by 2, okay? 1 by 2 positive, ln of 1 plus y squared plus ln of 1 plus x squared, okay, equal to c. Now multiply by 2, it will be 2 here, and this guy multiply by 2. This will be what? This will be ln of 1 plus x squared time, okay, 1 plus y square, okay, equal to c. Okay, it's a constant time a constant. This will be a constant again, okay, and this one can be reduced also, okay, can be reduced. So the solution will be something like this, okay. You have just to do this one. This will be 1 plus x squared times 1 plus y squared is equal to Euler to the power c. So this will be 1 plus x squared and 1 plus y squared equal to c, because Euler is also a constant. Okay, now we are done. Let's jump for another exercise, for another one. The second one is this one. Okay, suppose we are having dr, okay, dr is equal to ar sinus theta d theta minus cos theta d theta. Sorry, cos theta dr. Okay, cos theta dr. Now it's okay. Let us solve this one. We know applying separable method, first condition must be checked. So it will be dr equal to a, just multiply this and this and this and there. Okay, this and this. So what you're going to do, ar sinus theta d theta minus a cos theta dr. It's okay. Now just try to put all together, similar terms all together. Dr come here. What we are going to have, dr plus a cos theta dr equal to ar sinus theta d theta. Is that okay? Nice. So r in r will be 1 plus a cos theta. It is taking dr common, and here you have ar, okay, ar sinus theta d theta. Is that okay? Now where we find theta, okay, the function of theta, okay, the function of theta must go with differentiation of theta. The function of r must go with differentiation of r. So this will be dr upon the same r. And here this come here. This will be a sinus theta d theta upon 1 plus a cosinus theta. Okay, now I have to apply integration both sides. Okay, this integration we know it is ln of r, and this integration what will be this a, okay, a and this one. Just look this one, you will see that if I take minus here, took minus here, and this is the same as cos theta. Okay, 1 plus a cos theta. Okay, this differentiation here, this sinus, it is differentiation of a cos theta. If I differentiate a cos theta, the derivative of a cos theta is minus, okay, it is minus sinus theta, minus a sinus theta. That's why I put here minus, and this is sinus, this is the complete derivative. Just apply minus here and take minus out. Okay, yeah, and here you get this derivative and this one, so take this minus. This will be also ln, here negative ln of 1 plus a cos theta plus c, and here it is ln of r. So okay, but here also you can use what is the method, substitution method for this integration. Okay, it will work out also, and this can come here. You got ln of r plus ln of 1, okay, ln of 1, 1 plus a cos theta, okay, a cos theta equal to c. This one is the same as ln of r plus, this multiplication, plus r, we can say a first, a r cos theta, okay, okay, and this is c. Now if you apply Euler, okay, Euler here, it will be this one, r 1 plus a cos theta, okay, and here we apply also Euler to the power c. This will be what? It will be r 1 plus a cos theta equal to, Euler to the power c is constant also, so equal to c. This is the general solution for this equation. Okay, for this equation the general solution is this. Okay, hope it is fine. Now let us go for the third exercise. Okay, the third exercise, it says that suppose we have dy dx, okay, and it is Euler to the power x plus y plus x squared Euler to the power x cubed plus y. Is that possible to just applying separable method for this one? Yes, it is. Let us try then. So here, what else you have to do? Here you have just to skip this one, separate this one, okay? So it will be Euler to the power x times Euler to the power y. If you see this y and this y can be gotten as a common factor, this Euler to the power x. So plus this one square and this one to the power cube, okay, power cube times Euler to the power y. So as you can see, Euler to the power y will keep this one, and here it is comma, Euler to the power y, Euler raised to y is common factor, so I'll get Euler raised to x plus x squared Euler raised to x cubed. Okay, this is dy upon dx. Okay, now what you have to do, so this one as it is, we have just to reallocate, okay, function of y with dy and function of x with dx. So dy upon Euler the power y is equal to Euler raised to x plus x squared Euler raised to x cubed dx. Is that okay? Now what's the next step? Next step, just applying differentiation. Just try to differentiate them. This and this, okay, this is the same as Euler to the power minus y and dy, and this one, yeah, you can just apply differentiation of this one. This will be integration of Euler raised to x dx plus integration of x squared, okay, x squared Euler raised to x cubed and dx. Now see, this is x squared. This integration we know, this is euler to the power x directly. And this integration, if you see the differentiation, this one x squared is differentiation of this guy upstairs. Okay, if you see the exponent, this one will go this. So just put 3 here and take 3. Okay, then this will be easy to you to solve. This will be 1 by 3. Okay, d of Euler x cubed. And here we know this will be minus Euler to the power minus y. Okay, so it will be Euler to the power x, and it's all past c. Okay, then plus 1 by 3 Euler x cubed and plus c. And here it will be minus Euler minus y. Okay, now as you can see here, okay, you can just reduce this equation. You can reduce this equation just if you feel like, or you can just let it as it is. Okay, let this as it is, and this is fine. Okay, this is the general solution for this guy. Okay, this is the general solution for this, and you can stop there. Okay, you can stop there, but if you feel like, you can move on. You can just come here and apply ln of this and ln of this. Okay, ln of this. So you can just start work on it, and that's all. Okay, but here it's okay, because to apply ln of everything here, it will not work out. So yeah, it will not work out. If you apply ln of this, we know that to apply ln of a, it is possible only when a is greater than 0. So minus Euler, it is less than 0, so it cannot be possible. So this is the solution for this exercise. Okay, okay, let's jump for the next exercise, this one. And yeah, we will start for this one, then we can go for this one. Okay, this one will be the last one, if you feel like. No, we'll start for this. Okay, no problem. This one also, suppose we have yeah, we are still solving. Okay, suppose we have this x plus y and dy is equal to dx. Can it be solved also okay, like with separable method, like this? Can it be solved like this, applying separable method? The answer is yes. Sometimes when we have a question like this, we can also apply separable method. But how can we make them look like the same function of this? Like suppose we have to reduce like this. Dx must be a function of x and a function of y for this case. Sometimes it is not possible directly to get this one, as in this equation, or in the other one, it's like x plus y dy equal to dx in these both equations. Okay, it is not possible to get y in function like dy dx and fx and f of y. So what do we have to do in this kind of situation? If we want to solve, okay, applying a separable method, what we have to do is just take common x plus y. Okay, take common x plus y and do the substitution. Okay, let us first start with this one. Suppose this x plus y function like this, x plus y. Take this common. So what you are going to have, if you take this common, you have x plus y must be equal to, I will call v. Okay, call v. I'm solving this one, x plus y dy equal to dx. Okay, v. Then what we are going to have, x plus y is equal to v. So if this is true, now I will differentiate them. Okay, differentiate this and this, apply derivative of this with respect to x. So what we are going to have, d of v, okay, with respect to x. So what will be here? This will be, if I derive this guy with respect to x, it will be 1, and it will be dy dx. Okay, now it means that dy dx will be equal to dv upon dx minus 1. Okay, now my substitution will be based upon these two equations. Okay, let us substitute them. What we are going to do, substitute. Where I find x plus y, I will put v. So here I'll get v, okay, and here we have dy and equal to dx. Nice, dy equal to dx. So dy equal to dx, it is the same if as I just divide all the expression by dx, like dx, dy dx, divide here by dx, and here I will get 1. Okay, yeah, because if I divide here also by dx, I will get what? V, and here it will be dy dx. Okay, let me just do this again. See, we are going to substitute. The equation is x plus y is equal dy equal to dx. Is that okay? Now see. If I substitute, if I divide everything by dx, what you're going to have xy dy upon dx is equal to 1. Now you can substitute, okay? Now you can substitute star, okay, 1 star and double star in this equation. So what is x plus 1? X plus y is v. Dy dx is what? Is dv dx minus 1. Minus 1 is equal to 1. Are we together? Yes, we are together. So what's the next step? The next step is just to, okay, you have just to find this one. This will be v dv, okay, upon dx, okay, minus v equal to 1. This time this and this time this. Now what's the next? So we have just to reaggregate. This guy can go there, okay, this one, this expression here can go there, okay, and this go there also. This will be v dv upon dx equal to 1 plus v. It's okay. Now it's okay. So v dv, okay, this dx can go there, okay, this will be 1 plus v dx. Now everything that have v must go with dv, so it will be v dv upon 1 plus v equal to dx. Okay, now it is easy, you can just integrate and integrate. Okay, it's by integration both sides. What you are going to have, this integration both sides. Okay, see, it is v, right? Yeah, you can just do this one. This is the integration. Actually, let me pick up another paper here. Yeah, so we have integration of v, okay, v dv upon 1 plus v equal to integration of dx. So what is the step to solve this integration? See, this is 1, right? It is the same as I write 1, okay, v plus 1 minus 1, okay, and this is dv, the same, okay, all upon v plus 1, and here dx we know it is x plus c. Now see, this and this will be one integration, v plus 1 and v plus 1 dv, and here minus dv upon v plus 1 is equal to x plus c. Okay, v plus 1, this will be 1, integration of this guy, this will be dv integration, minus this integration here we know, this will be what? This is the same as d of v plus 1 and v plus 1 equal to x plus c. Okay, this integration is v minus, and here ln of v plus 1 equal to x plus c. Now what do we have to do? Okay, now what do we have to do? That's the point. Here, okay, what we have to do? Yeah, what we have to do, just this is the equation actually, okay, this is the solution for this equation, and yeah, you can finish like this. It's finished. So sorry, we have to be back to the substitution. We said that v is equal to x plus y, So just substitute. This will be x plus y, okay, minus ln of x plus y plus 1, okay, equal to x plus c. Okay, so what you're going to have, this x and this x will be cancelled out, will be y minus ln of x plus y plus 1, okay, equal to c. Yeah, this is the solution. Yeah, sometimes it is not directly said, or you cannot, how can I say, you cannot just transform the equation in this form, but you can apply substitution. So this substitution will help you to solve this equation, to solve this applying this method. Now the last question is this. Okay, this is an exercise that came also in a GTU paper. This one, cos of dx dy equal to dx. Okay, they mark these three values. So what is the point here? The point here is that you have to see the only thing that you have is x and y. This is a one point. Okay, you can solve this one point. Okay, again I will just repeat you. Okay, you can solve these equations. Okay, even this equation that we solved here, this equation, okay, I'm solving with separable method because we are speaking about separable method, but I can also solve with any other different method as long as this is acceptable. Okay, as long as the condition is satisfied to the method that I'm choosing. Okay, for this exercise, suppose we have this one, we can solve also with separable method. Okay, how? See, we will do the same. Here x plus y, we can do x plus y equal to u. Okay, u or v, it's okay. Now the next step, apply derivative. Okay, d. Okay, try to derive this expression with respect to x. Okay, and here du. Okay, dx. So what we are going to have, this will be 1, okay, d1 dx 1, and dy dx, this will be dy dx equal to du dx. Nice. Okay, this one shows that dy dx is du dx minus 1. Okay, I'll call this double star, and this one I will call this star. Okay, now we'll substitute this star and double star in the main equation. So we are going to have cos, okay, of x plus y dy equal to dx. We will divide here by dx and here dx. Okay, so what you're going to have, cos of x plus y, okay, dy dx is equal to 1. Okay, we will do now we will substitute this in this equation. It will be cos of u, okay, then here it will be du dx minus 1, and here equal to 1. Now from here, whatever you have to do is just to find cos of u du dx minus cos of u is equal to 1. Okay, this expression here have this cos and this cos. Okay, so just put this one out. This will be cos of u du upon dx is equal to 1 plus cos of u. So this will be 1 plus cos of u dx, and here cos of u du. Okay, du. So what else? You have to put everything that is remaining in u must go with u. Okay, u come here, function of u come with differentiation of u, 1 plus cos of u and du, and here it is dx. Okay, just like this. Now you can apply integration here and integration here. Okay, now what is the next step? We get an equation like this. Okay, cos of u du upon 1 plus cos of u equal to dx. Differentiation. So what is the next step? C. We know here we have to apply the substitution, okay? Or you can just directly do the same, like see, this is cos of u, okay? Cos of u, add 1, okay, and take 1 minus 1. This one, okay? You can do this, add 1 and take 1. It will be simpler to you. If it is simpler to you, it's fine, okay? You can do this, or you can directly find just applying some shortcuts, okay? Some shortcuts, like we know, I will solve this completely. See, to solve this equation, whenever you see cos of u and the fraction of cos of u the same, you can just remember, you know that cos of u is equal to cos of u, okay, u by 2 plus u by 2. Is that okay? Is that correct? Now we know that cos of u by 2, this summation, it is cos of u by 2 square minus sinus of u by 2 square. That's 2. Now what we are going to do, if I come here and if I divide this, I will divide this by cos square of x, of u by 2. Divide by cos square of u by 2 in here, okay? And the same that you came here and divide, and do the same here, okay? Okay, you are just, it's like multiply this by, sorry, I'm just making confusion here. Let us write here, okay? We have cos of u, it's equal to cos of u by 2 plus u by 2, okay? And this is cos of u by 2 square minus sinus of u by 2 square, okay? Now, what you're going to do, multiply, okay, multiply by sec square of u by 2 and divide by sec square of u by 2. What we are going to have, we are going to have cos of u, it is the same. If you divide, this sec is 1 upon cos, 1 upon cos. So 1 upon cos here, it will be 1. 1 upon cos, this will be tangent, okay? Tangent square of u by 2, okay? Tangent square of u by 2. And this one, tangent square of u by 2. And here, sec square of u by 2. What is sec square? We know that sec square of u by 2 will be 1 plus, okay, 1 plus tan square of u by 2, okay? Because we know this formula. I hope just you know, because what we are going to do is just substitute in this, okay? We are just going to substitute this equation there, okay? This is what we are going to do. So here it is the same, sec square, it is the same of 1 plus tan square of u by 2, okay? There's 1. So it means that I can write cos of u in a function of tan, okay? So whenever I have this kind of integration, I can just do this kind of substitution. I will do u, okay, like this is cos of u, so I will do tan of u, okay, tan of u, like tan of u by 2 is equal to t. It's here. Tan of u is equal to t. It's okay. U by 2 is equal to t. This is the kind of substitution that we do here. Okay, when we see cos of this and blah blah blah. So what does it mean? It means that if I have cos of u du 1 plus cos of u, okay, equal to integration of this, So I will just have to do this one. Tan of u by 2 will be equal to I can say t. Okay, t. U by 2 is t. If tan of u by 2 is t, so what does it mean? If I apply integration for this guy, okay, if I apply integration for this guy, or I can do anything like if I apply, not integration, sorry, derivative. If I derive this and this, if I try to apply just a differentiation of this guy, it will be what? It will be 1 by 2 and sec square of u by 2. Okay, and this is equal to dt. Nice, it's fine. Now sec square of u by 2. What is sec square of u by 2? That's the point. Sec square u by 2. Sec square, it is the same as 1 plus t. Okay, this is the same as this is this expression here. Just grab this expression. Now the second is as long as we have this one, now we have to substitute. Where I find cos of u, I will put 1 minus t square upon 1 plus t square. Where is it coming from? Do you remember this? Okay, so t is what? T is tan of u by 2. That's why it's 1 minus t square and 1 plus t square, just like this one. Just so this one. So just substitute this expression in there. What you are going to have, that's the point. Yeah, what you are going to have. This expression here can also be written in this form. This is sec of this one. This can be also 1 plus tan, because sec square, it is the same. Tan of u, this one square. Is that okay? Yeah, du. This is equal to dt. Okay? Du. Sorry, I forgot here it is du. But it's okay, no problem. So sec square of u by 2, it's the same of this. Okay? And yeah, just by looking at this, directly you can see that this one is the same as t. Okay? It is the same as t. So you can just stand this one or just send him out there. It will be 1 by 2, 1 plus t square du and dt. You can just send this one there. This will be what? This will be du is equal to, will be equal to what? Will be equal to dt 1 plus t square, and these two come here. Okay, this is the same. This is the same. Okay, yeah. Let us substitute then. Where we find du, we will put 2 dt 1 plus t square. And where we find this cos theta, we will put this one. So this will be integration of this cos of u. What is cos of u? This is 1 minus t square upon 1 plus t square. Then upon 1 plus 1 minus t square upon 1 plus t square. Then ddu. What is ddu? Ddu, okay, ddu is 2 dt upon 1 plus t square. Okay, this is the expression. Now we have just to find here, to find out the common denominator. If we find the common denominator here, what we will end with, this minus and minus will be down, so you will end with this kind of expression, this one. These and this we're going to cancel out after finding this. Down here you have only 2, and you are here, and you get 1 plus t square. Okay, 1 plus t square, and here you will remain with the 1 minus t square 2 ddt. Okay, these 2 and these 2 will be cancelled out also. This will be 1 minus t square upon 1 plus t square dt. Okay, now how to solve this expression? Okay, how to solve this expression? This expression will be the same as, okay, the same as, we have just to add, okay, like this one. Suppose here we have this one, it will be 1 minus t square minus 1, Okay, I'm adding minus 1 and I have to take plus 1. Okay, plus 1. Then this plus 1 here will be 2 upon 1 plus t square dt. Now what you are going to have in here, this will be integration of 2 1 plus t square dt minus this and this will be t square plus 1, and here t square plus 1 dt, this and this. So this will be this integration, this will be 2 upon tan inverse of t. Okay, this is tan inverse of t minus, here it will be only t. Are we together? Yes. Okay, hope you're not lost. So this will be t. Now it means that this will be integration of cos of u, 1 plus cos of u du, integration of dx. This will be x plus c, and here it will be 2 tan minus 1 of t minus t. Okay, from here. Now we have to be back to the substitution. We say that t is equal to tan of u upon 2. And we say that u is what? U is x plus y. Substitute just. Then I will get 2 tan, okay, 2 tan inverse of tan of u. What is u? X plus y upon 2 minus, this is t. What is t? We say that t is tan of u. What is u? Tan of u upon 2. So what is u? U is x plus y all upon 2 is equal to x plus c. Okay? Yeah. Is equal to x plus c. Here I'm just substituting, okay? 2 tan inverse of t minus t and so on and on. Just substituting this. So tan, here I have this one. This is the expression. Here 2 tan inverse of tan x plus 2 upon 2. What you have to do here, this one, whenever I have tan inverse of tan of x, it's equal to x for any value, any x, okay, for any value or any x. So this will be 2, okay, 2 will be this expression only, 2x plus y upon 2 minus tan of x plus y upon 2 equal to x plus c. Okay, yes, you have this expression. Now see, these 2 can be cancelled with this, and this will be only like x plus y minus tan, okay, tan of x plus y upon 2 equal to x plus c. This x and this x will be cancelled out. So the solution will be this one. Will be y minus tangent of x plus y upon 2, okay, x plus 1 upon 2 equal to c. Yep, this is the solution of this equation. So I hope it can be helpful for you. So now we are done with this separable method for solving first order and first degree differential equation. So thank you. Just drop your comment on everything you feel like you didn't understand, or you can just directly write in the comment any step or any path that you feel like there must have some misunderstanding or any suggestion and thing like that. Thank you. We see you and see you when I see you. Bye.